Hi, everybody. Welcome. Today we're going to be talking about scatter plots and linear regression. In earlier classes, you may have heard of something called the line of best fit, and that's where you make a scatter plot with data that has been collected and then draw a line. You may have estimated the equation of this line that would fit through the middle that would best fit all the points. Well, today we're going to be a little bit more precise, and we won't be calling it a line of best fit, but it'll be called a linear regression line, or even more specifically, a least squares regression line, but we'll get to that later. First of all, we want to start off with scatter plots. Scatter plots are when you take some data that's been observed, like we have right here. I've got the maximum noise level decibels plotted vertically and the number of thousands of people. And so we need to know which variable is the explanatory and which is the response. The explanatory you can think of as being the x variable, and the response variable you can think of as being the y variable. And in statistics, we label them this because the y variable, or the response variable, responds to the x, the explanatory, or the explanatory variable explains the response. So in other words, the number of thousands of people would explain the maximum noise level in decibels. Now we will be given some scatter plots, and then we'll be asked to describe the scatter plots. Anytime you're asked to describe a scatter plot, you need to identify four aspects: direction, unusual features, form, and strength. The direction, you will label that as either the line or the trend is that the points tend to go up, or the points tend to go down. If they tend to go up, we'll call that having a positive direction. If they tend to go down, the direction would be negative. Unusual features would be points that either don't follow the pattern in other words, points that aren't really doing what all the other points are doing, or gaps in the data. So you might have a whole bunch of points that are together, and then this little lonely point on the other side. That would be an unusual feature. Form, I want to know, is the form of the points, does it make a linear form? Like, do all the points tend to travel up or all the way down, or do you see more of a curved form? Do they go up and then come back down and maybe go back up again? And strength, you can think of as how close the points are together, or how close the points fit the pattern. So we've got some examples here. I'm going to label these example A, example B, and example C. And we'll start with example C. So I'm going to describe all the key aspects. So I need to describe the direction, unusual features, form, and strength. And it looks like duffs when you write it out. Okay, so the direction, if I were to look at these points, I can imagine, let me try to draw a better line. I can imagine that there would be a line that goes pretty much through the middle. To me, it looks like that line is going up. So I'll say the direction is positive. Unusual features, I don't really see any points that are way up high or way down low, or any points that are not going along with the pattern. So I would say there are no unusual features. The form, Looks to me like this is linear. The points tend to go in a straight line, so I would say linear on this one. And the strength, all the points are pretty close to the line, so I would say this would be a strong relationship. So this scatter plot has a positive, strong, linear relationship with no unusual features. The second one, if I were to imagine, I would love to make this be a line. So let's see, if I try to draw one here, then I can, if I look at this group of points, whoops, I didn't mean to erase that. I meant to draw. If I draw a line there, then I could say, well, for this group of points, I see a linear association because they seem to be kind of going in that linear pattern. But then this extra point seems to be an unusual point. It's not doing what all the other points are doing. So I would say it's kind of weak. So I would say moderately weak. It's not super weak, but it's kind of weak. So moderately weak, negative, linear association or relationship with 1 point above all the rest. Then if I go backwards to part A, I see this scatter plot, and I try to imagine where a line could go through the middle, but if I look at this, I kind of see two things. I've got this, and while I could just graph this middle section and ignore those two, that's 4 data points to ignore. So that's a lot. I don't want to ignore 4 data points. 1 or 2 is okay, but 4, when you don't have that many to begin with, is a lot. So I could say, okay, well, I see this positive association right there, but then at the same time, you might be able to draw one that way. So it's really unclear if we have a positive or negative association. So since it is so unclear and it's very hard to tell, we're going to say this is a weak association. And it is too hard to tell if it has a positive direction or negative direction. So we're going to say no direction. Really no form. And unusual features, everything is kind of just doing its own thing. So it's a weak association, no direction, no form. Now, it is possible that one person would interpret just a little bit differently. Like I might say moderately strong, moderately weak. But as long as you justify and give an explanation, you should be okay for our class. So now let's kind of go a little bit deeper into this idea on strength, because we have a measurement of strength, how close the points fit the pattern. It's called correlation. Correlation, also known as the correlation coefficient, is a numerical measurement for a linear relationship. Now, if it's curved, this correlation coefficient, or otherwise known as R, is not really applicable. But if we have a linear relationship, we can use R to determine how strong that is. So we can estimate the value of R, but we'll use a calculator to actually determine it. And what we're looking for in a super strong relationship is that the absolute value of R to be close to 1. That means strong relationship. And then I have some pictures right here of different values of R. So if R is 1, like in figure D, then that means all of the points are on the line that you come up with the equation for. And the slope is 1. If r is equal to -1, all the points are on the line, and the slope is -1. And those would have equal strength. So we've got -0.94, still strong. 0.86 is not as strong as the -0.94, but it's still strong, so we could call that moderately strong. These R values are close to 0. Another thing you might see is that you might see all the points just randomly scattered around. That R would also be close to 0 when there's no relationship. So we'll calculate R in a little bit. But that's another way that we can double check the strength of the relationship in our scatter plot. So now let's talk about actually calculating that regression line. So the regression line is the line that's calculated that describes the predictions. So it's a model for the data, and we can use the model to make predictions for what would really happen. And so you might see it in the form y hat equals a plus bx, but really you can think of it as y hat equals mx plus b, where m is the slope, b is the y-intercept from your earlier algebra classes. You might also see it where the b is written first, y hat equals b plus mx. And you hear me saying y hat, and I really am. I'll write it out so you know that I'm really saying y hat. That little caret on top of the y, we call that y hat, and it means the predicted y value. Not the actual y value from the data that we got collected, but it's the predicted y value. The b would be our y-intercept, and the m in this case would be the slope. So now we're going to calculate our own regression line. We can do this with Desmos. And if you've got a copy of these notes, then if you look at the very back of the notes, I'm going to scroll all the way down, there's directions, step-by-step directions on how to make your scatter plots and line of best fits and residual plots, which we'll talk about later, on Desmos. If you don't have this, then you can take a screenshot right now and refer to it later. Okay, so let's go back and we'll make our own scatter plot. So I have this data. First of all, I want to get familiar with the data. It's for the weight of ice cream sold at a small store in pounds. And I like to always label so I'm sure of what I'm talking about. So X is the weight of ice cream in pounds. And Y is the temperature outside in degrees Celsius. So the first point, 26, means that the ice cream store sold 20 pounds of ice cream when it was 6 degrees outside. The ice cream store sold 17 pounds of ice cream when it was 3.5 degrees outside. So we'll look and see what the relationship between these two would be. I mean, I would think the store is not going to sell much ice cream when it's cold, but you never know. Let's look at the data and plot. So I'm going to open up a Desmos tab, and I'm going to plot that whole table. Just let me get everything all situated. Let me pull my numbers over here. Slide my Desmos tab. All right, so there's my Desmos. So I've used Desmos. I've entered the chart on Desmos, and you can pull that up by pressing the plus sign and choosing the table feature. Type it in. Then to get my linear regression equation, I'm going to type in y equals mx plus b. But nothing really happens. Oh, by the way, we'll do that again. When I typed in my points and I zoomed to the correct window, I can see the scatter plot. So it looks like as the weight of ice cream sold increases, the temperature outside increases. So they sell more ice cream when it's warmer. All right, back to getting the regression equation. I need a second line. If you type in y equals mx plus b, you're really close. Problem is I want to use the data from x1. So instead of y and y1, so instead of y, I'm going to have y1. Just type a 1, and that 1 pops up automatically. And mx, I'm going to type an x1 to use the table. I'm going to pause the video to make that all come right back. Oh, and instead of equals, I need the little tilde accent. You'll notice my regression line gets plotted, and then I'm given parameters. So I see my slope is 0.782, and my y-intercept is negative 9.435. So I will put those on my notes here. Use technology to compute the best fit line. All right, so I will say y hat equals 2 decimal places. Okay, so 0.78x minus 9.44. And then the second question says, what are the slope and the y-intercept for the best fit line? So let's talk about the slope first. The slope is 0.78. And slope is rise over run. So slope is rise over run, and my rise is the y, right? So as the temperature increases by 7.78 degrees Celsius, we see that our weight increases by 1. Or we can say it the other way. As the weight sold increases by 1 pound, the temperature outside increases by 0.78 degrees Celsius. The y-intercept in this case, oh, and by the way, this is on average. I should emphasize that this is on average because it's not what actually happens, but it's what we predict, what we see happens in general. So on average, every time the store sells 1 more pound of ice cream, the temperature outside increases by 0.78 degrees. The y-intercept in this case is 0, negative 9.44. Remember, 0 is the weight, and negative 9.44 is the degree Celsius. So we can say when the store sells 0 pounds of ice cream, the temperature is, and we need to say predicted to be because it may not be what actually happens, but it's predicted to be what's it predicted to be? Negative 9.44 degrees Celsius. The next question says use the line of best fit or the best fit line to predict when the value is 10. So I will look and say, okay, when the value, so this should be when x value is 10. So I'm going to substitute 10 in for x. So I'll say y hat, the predicted y, equals 0.78 times 10 minus 9.44. I'm going to substitute that into my calculator and see what I get. 78 times 10 minus 9.44. So my predicted temperature is negative 1.644 degrees Celsius. So we're predicting that when the ice cream store sells 10 pounds of ice cream, the temperature outside is negative 1.644 degrees Celsius. Second question is really interesting. It says, is this a good estimate? And you're like, well, I mean, I used the formula, is it? This is where we look at the range of values that we have and where they're asking me to make a prediction. So I'm going to pull my Desmos back up, and I'm going to add, I'm also going to graph the point that we just estimated. 10, comma, negative 1.644. So I want you to see what happens, where it shows up. So notice all of the points that I was given are all the green points on the screen. Those are the observed values. You can think of those as what actually happened. Like we went to the store on this day when they sold 18 pounds and saw that it was 5 degrees Celsius. And then we went to the store and saw that they sold 19.5 pounds when it was 6.5 degrees Celsius outside. So those are the observed values. The line is what we would predict to happen. Sometimes we're off, but like right here at 21.7, our prediction is pretty close to what actually happened. But we are using this information to predict the temperature for data that's really far away from the other points. And that's really not a good thing to do when you're using linear regression. Ideally, what we would like is we would like our predictions to be within this window of observed values because we have some real data to back us up. But when we extend our predictions beyond the scope of what we see, that's called extrapolation. And that is not a good thing to do with linear regression because we're not exactly sure what happens before that 17.3.5. So we don't want to do that. So the answer to that question, is it a good estimate for the data? We're going to say no. That causes us, or that causes us to extrapolate values. That means make predictions outside of what you know to be true. And extrapolation is not a good thing for what we're doing today. So you want to keep those predictions for pretty much between these y values. That's what we want to do. All right, moving on. Now let's talk about something called a residual. A residual is the difference between the y value on the actual scatter plot and the predicted value by the linear model. And so we can think of this as being the residual equals the actual value we observed minus the predicted value. And so if I look back at my Desmos example, I have what actually happened at 19.5, but then I can use my, let's see, 19.5, but then if I use my regression equation to make a prediction at 19.5, I would do my mx plus b, so I would do 0.78 times 19.5 for x. I'll need that one. Plus my y-intercept here, was negative 9.44. And then I'll plot that point as well. So we predicted at 19.5, we got 5.77. Okay, you can kind of see that purple dot show up on the line. So predicted at 19.5, I got 16.5 for the degrees outside. No, that was actually what happened. It was actually 6.5 degrees outside. But we predicted 5.77. So our prediction was a little bit lower than what actually happened. The difference between those two, the 6.5 and the 5.77, that is called a residual. And so you can see that kind of drawn here. The point on the line is the predicted value. And then the point at the top, that's the observed. Or it might be below, depending on if you have an overestimate or underestimate. What actually happened. Okay. And then we can take all the residuals for each individual point and make something called a residual plot. So let me talk about a residual plot. Let's see, where's my Desmo screen? There it is. Residual plot. So I'm going to take all of these off here. Okay, so once you have calculated your regression equation, I can click this under residuals, and it will calculate these numbers right here are my residuals. And you want to delete that row. Let me pause this for a second. All right, so I've deleted that column. Let's look back at that. Okay, so what's plotted in this column, the red E1 column, those are the differences between the observed values, these 6 values, the 6, the 4.5, those values, and the points that appear on my line, the Y values on the line. So it took the point on the line, and it subtracted it, and I got these residual values. What we want to see in residuals, if you notice on my scatter plot, I've got some points above the line of best fit and some points below. On the residual plot, which is right here, it takes the residual values and it plots them against your explanatory variable. So we've got the values of the residuals, and then the X value is the pounds of ice cream here. We use the residual plot to determine if the relationship that we formed with our y equals mx plus b equation, if that is a good model. Here's what we want to see. We're going to look at the residual plot, and what we want to see is that the residual plot shows no obvious pattern. So we want to see a pretty random pattern there. We also want to see, we don't want to see a curved pattern. The residual is pretty small in size because we want to see that our predictions were pretty close to what actually happened. And the sum of the residuals should be 0. Now, I'm not asking you to add up all the residuals, but you can observe on the residual part to see, okay, well, I've got a point up here and a point down there. And if I add those two y values together, it's kind of close to 1. So you can kind of visualize there should be some above and some below, and they kind of cancel each other out when you add them all together to be 0. So that's what we want to see. Now, here's a couple of examples. Here's what we can tell. So we're going to skip past this example for right now. All right. So here I see a scatter plot on the left. And at first, it looks like, hey, that might be a linear model. But then when you examine the residual plot that goes along it, you can see that the points kind of follow a curved pattern. So that tells me the scatter plot that the linear relationship is not appropriate. Relationship not appropriate. So maybe instead of a line of best fit, I might want to do a curve of best fit. Maybe a quadratic, polynomial, power. The second example, I can see clearly the scatter plot has a curve, and also the residual plot is also curved. The last example is a nice example of a linear relationship because the scatter plot looks like it would make a linear relationship, and the residual plot is pretty random, no pattern. All right, and so that concludes our lesson for today. Let me know if you have any questions.